One of the many research projects we have going on at Wright State University focuses on plain old ordinary wood. Now, wood isn't the best material in modern times, but it's still got certain advantages. It's cheap, it's plentiful, it's renewable. It actually also has a fairly good strength to weight ratio in comparison with other engineering materials, but we'd like to make it even better. So what we're doing here is we're taking samples of wood and we carefully chemically treat it to remove a precise amount of the lignin in the wood, leaving behind a higher fraction of the cellulose nanofibers which give the wood its strength. We then use a combination of pressure and temperature to compress the wood and bind those strengthening fibers together even stronger than you see in natural wood. This results in taking a piece of poplar like this, which has a strength of about 50 megapascals, and it becomes a material which has a strength of 350 megapascals. That's a 7-fold increase in strength. That's pretty significant. That means that we can make a wood-based material which has strength that is on par with a lot of structural grade aluminums. So that's interesting from an engineering perspective. So I'm going to turn the rest of the video over to Victor Pushparaj. He's the student that's been working with me. He's been at the forefront of this project and he'll walk you through some of the details.
Step 1, sample preparation, but safety is a must. Step 2, boiling the sample in the liquor solution, and it has water, sodium hydroxide and sodium sulfate, and that's my sample. I'm going to boil the solution at high temperature. Step 3, after boiling the wood in the liquor solution, we're going to compress the wood using this equipment. And this is a specially designed plate. We have wood inside this chamber. These are the heating plates and this is the heating box. This wood is being compressed simultaneously and also being heated at 100 degrees Celsius. After successful boiling and compression, we were able to reduce the thickness of the raw wood sample. This is before boiling and before compression. This is the wood sample after boiling and after compression, and see the change in the thickness of the wood sample. To identify the strength of the compressed wood, we're going to do a mechanical testing called as a 3-point beam bending test. That tells me what's the strength of the material. And this is the 3-point beam bending equipment, and it's also a software control. I'm going to start the test. If you can see here, these are the 3 points, point 1, point 2 and point 3, and this will apply load on the wood sample and the data will be recorded by the computer. My next step in material characterization is looking at the microstructure of this small piece of wood. To do so, I'm going to use this equipment. This is a high magnification scanning electron microscope. This helps me to really zoom in terms of micrometer or in terms of nanometer. To do so, first I need to load the sample in this equipment. And after a certain process, I was able to capture a few images from that wood. This is the microstructure of the raw wood which hasn't been compressed or which hasn't been treated in the chemical solution. And this is the microstructure of the wood which has been treated in the chemical solution and has been compressed. And observe the change in the microstructure where the cells has been collapsed.
So this project isn't finished yet, it's still ongoing. We're still working to improve the strength of these wood materials even further and other properties. For example, weatherability is very important in engineering materials like this. So for those of you who remember your chemistry, we're trying to accomplish this by chemically cross-linking the cellulose fibers of the wood in order to stabilize the structure, in the same way that people cross-link the rubber in tires in order to improve its mechanical properties. So thanks for watching. Hope you learned something.